So the next thing that we're going to talk about is the systems of units. Units are very important to engineers. There's a huge difference between a foot and a meter. And as engineers, a lot of the stuff that we do are going to be based around different kind of units, mixing of metric and English units. And I take units very seriously, especially when I grade. If you think about it, one of the biggest examples of a complete screw-up that I can think about would be in 1999, NASA developed a satellite to land on Mars and do some studying. Raytheon was given the contract for the software. NASA told them to program everything in metric. So Raytheon did, handed over the software for the probe to NASA. NASA ran all of their stuff in English. And so when the $300 million probe was descending into the atmosphere of Mars, since it was figuring it would be firing its jet at a height in meters instead of a height in feet, well, it wasn't enough to slow it down. And so our $300 million probe became an interplanetary ballistic missile and exploded on the surface because it was traveling too fast. So we take units very seriously, and so as we look at it, we do have three basic types of units. So we have SI, the international system. I would say it's Système International or something like that in French, but I'm absolutely horrible at French. So that's our first unit. We typically call those metric units, and so the base units would be length of meters, time of seconds, mass of kilograms, force of newtons, and absolute temperature would be in the Kelvin. A subset of that is what's called the absolute metric. You'll sometimes see this when you're dealing with smaller systems. Instead of using the meter second kilogram, it uses centimeter second gram and gives you a unit of force called the dyne. The next are the two English systems. British Gravitational, which would be the imperial units or just the English system. And you could probably hear that. That's my dog barking. That's what you get with live recording of videos. So the British gravitational system is based around the foot. The second, the unit of mass is the slug, and the unit of force is the pound force, and temperature would be degree Rankine. And then we have the English engineering system, which you'll see is pretty much the same, except for that distinction right there between the slug and the pound mass. This comes about to how force is defined, which is why those systems are a little bit different. So let's talk about, before we get to why that's different there and how we take care of it, let's just talk about force. And this is kind of important because it'll always help you remember if you forget, hey, what is the units of force in the metric system? How do they put that together? Or the English system, because we are going to be concentrating these guys into little boxes as we go along in this class, is force is defined by F equals ma, Newton's second law. So any of this would be 1 unit of force in the metric system, that would be the Newton, is equal to 1 unit of mass, which is a kilogram, times 1 unit of acceleration, which would be a meter second squared. So if you ever forget exactly what a Newton is, you can sit there and go, okay, well, it's F equals ma, I can calculate this out. Conceptually, how big is a Newton? A Newton, I had a physics teacher when I was an undergrad that would always say, McDonald's made a huge mistake because they really could have helped with teaching Americans the metric system because of one of the burgers. So back in the Stone Ages, when I was in college, McDonald's introduced the quarter pounder with cheese. And my physics teacher liked talking about that, saying they should have called it the Newton burger, because 1 Newton of force is about equivalent to a quarter pound. Now that sounds really stupid, but you'll never forget that now because it kind of gets squirreled away and locked into your head. So on the English side, the British gravitational, so we have the pound force is 1 unit of mass, which is a slug, times 1 unit of acceleration, which is a foot per second squared. The same thing holds true for the dyne. So the dyne would be a gram times a centimeter per second squared. And that's all because in all of those systems, force and mass are dependent on each other. So in the SI system, force is dependent on the mass. In the British gravitational system, mass is dependent on the force. English engineering, force and mass are defined independently, so we need a constant proportionality to have it work. So in the English engineering system, it's not F equals ma, it's F equals m times the acceleration divided by the gravity constant, where the gravity constant would change depending on what planet you're on. So the gravity constant for Earth would be 32.174 foot per second squared, pound mass per pound force. Now this is pretty close to 32.2 feet per second squared, so we can use that, to make it match up with the Earth's gravity. And it just makes things a little bit more difficult. I personally do not like the pound mass unit. I know it is used a great deal in thermodynamics, but I'm one that I like my units to be dependent on each other to make things a little bit easier. So, that is the end of our introduction to our units.